and welcome to another episode of FooBar. Today we have a really interesting episode. I went and I did an interview. It's been such a long time that I don't talk and I don't have a guest in here. So today we have Julian Wood. He's in my team. He's a senior developer advocate for the Serverless team. And he will come and chat with us about scaling Lambda. This is a topic I've been avoiding for a while, so I'm super excited to have Julian coming into the channel and telling us everything. So we were going in this video deep dive on the different types of ways that you can invoke Lambda, how scaling works for your Lambda functions, how you can take care of your account quotas and your burst quotas, things that you might have heard before, some tips and tricks on scaling your function, and all these type of things. We talk for an hour, so there is a lot of content there. So with that, let's get into the interview. So hello, Julian. Welcome to the channel. How are you doing?
Marsha, I am fantastic so much. I finally feel as though maybe I've made it in this world. I'm on FooBar Serverless. Like, how cool is that? I'm chatting to it's one of my heroes. Marsha, I'm great. I'm great. Thanks for having me.
I'm so happy that you're here because you're going to talk a topic I've been avoiding for years.
I'm glad I can help, maybe.
Let's see, because we all hear that Lambda can scale forever and ever, and serverless is magical, and we present it like this unicorn. And today we are going into the depths of how Lambda works, and particularly scaling and throughput and all these things that we take for granted.
Absolutely.
So I'm very, very excited, and I imagine our audience is as well.
Looking forward to it.
So first, just if somebody's living under a rock and they don't know you, who are you?
Well, I can't presume anyone knows me. Yeah, my name is Julian Wood. I'm actually on Marsha's team at AWS. I'm a senior developer advocate as part of the AWS serverless division, I suppose. I've been working at AWS for 3 years. I came straight into this job. It's an amazing job. I think two sides of the job. One is to help people understand how serverless works in general, and also particularly today we're talking about Lambda. And then also, we do a lot of work trying to get feedback back to product managers, feedback internally, what everybody out there is doing with, specifically today in Lambda. And so we can make the best serverless products and features and hopefully sort of get that flywheel working, that Lambda is even easier to use or even more scalable or even bigger, better, faster, more, whatever Lambda can do. Lambda can do more.
Yes, that's good. So let's jump straight into the first question. What concepts we need to understand in order to, from Lambda, in order to get started into scaling?
Yeah, certainly. Well, first of all, yes. just to know, Lambda is a massively scalable, massively distributed platform where you just upload your code into the cloud and we just run it on your behalf. Now, you may know that we just run it on your behalf, but the weird thing is that there are actually servers that these run on. There are actually servers in serverless. Secrets, I know. Oh, heresy. But yeah, we maintain, fleets of many servers, definitely more than one or two, which run Lambda on your behalf. And we sort of take on that responsibility of running the whole distributed part of Lambda. So you don't have to. So you don't have to become an expert in distributed computing. You can just send us your code and that becomes our problem. So all the sort of, as Werner in his keynotes often talks about, the compression algorithm for experience, for me, serverless is sort of the epitome of that, is all the things we learn about scaling these massive systems within AWS, we can run services like Lambda on your behalf.
Yeah.
So Lambda scales massively. I mean, we've got customers who run hundreds of thousands of concurrent Lambda functions. I'll explain what that concurrency means. But yeah, yes. You can do a huge amount with Lambda. It really scales pretty much as high as you're going to go. And then also coolly scales down literally to zero. So if a Lambda function,
and that's my favorite part.
Exactly. scales down to 0. If you're not using it, you're not paying anything. And it's just actually a really simple thing to, first of all, understand. The more you use, yes, the more you pay, but there's nothing to pay if you're not using it. And also there's really good sort of financial things you can build around it, that you can start to understand the sort of cost and economics of your individual Lambda functions and know how individual Lambda functions scale for different parts of your business. And when you've got that sort of direct cost correlation, that can give you some sort of other business insights, which you wouldn't necessarily get if you've got a huge, big application running on a whole bunch of servers. How do you know which different parts of that application affect your bottom line?
But for them, they need to tag their Lambda functions.
Yes, you definitely need to tag your Lambda functions, because one of the challenges with Lambda functions is you're going to land a building more and more and more and more, and you need to corral them, and you need to sort of care and feed them a bit so you can understand what they are. You don't have to give them individual names, although we'll name them for you, but they become your friends.
Yes. So then you mentioned concurrency. What is concurrency?
Well, actually, what I'm going to do is I'm going to jump into, I've got some slides because I'm a visual person and it's just slightly easier to explain these kind of things.
And I think a lot of these things are very visual, so
exactly.
It helps.
So if we sort of start at the beginning, the way a Lambda function runs is it sort of is invoked. And there's sort of two main ways that Lambda functions are invoked. One is with a synchronous response. So this is, if you tie Lambda together against an application load balancer or an API gateway, or even a function URL, or step functions, a whole bunch of things. And this is where you do a synchronous request. You call your Lambda function, it does some processing, and it waits. When it's finished its processing and it's got something to return to you, it then comes back. So obviously there's a waiting time. That Lambda function is going to run for as long as it can be, up to 15 minutes. And your whatever's calling that Lambda function just waits for the response. Now, it's not always 15 minutes for all things, because API Gateway has a limit of 29 seconds.
Yeah.
So, you've got a 29-second limit for synchronous invocations there. But something like function URLs, you've got 15 minutes. So that's a synchronous side. You're waiting for a request response. Very popular in web apps and popular in some of the other things like step functions. Then on the other side, when you start building event-driven applications, there's this asynchronous model. And this is super powerful in Lambda, where you ask Lambda to do some work for you. You don't wait for the response. Lambda just says, I got your request, sends you a 200 response, and off you go. And so if you're thinking of something like EventBridge or S3 up on the slide over here, you're going to write a rule in EventBridge. It is going to target a Lambda function. EventBridge is going to send that request to Lambda, and it's just going to get immediate response back. So even if your Lambda function is going to take 15 minutes to run, EventBridge isn't waiting for that. If you're doing it via your own, SDK or CLI, you're not waiting for that request. And then internally, Lambda actually just puts that on a queue. It's an SQS queue. We build Lambda on a whole bunch of AWS primitives, and then the Lambda service then pulls that queue and then invokes your Lambda function. Can take up to 15 minutes. And then obviously there isn't a return path that it's going to be able to send that request, back to what called it. So it's, but there's going to be some asynchronous notification that's going to happen that is going to basically
you need to build that.
Yeah, and
if you need
to build that. And then there are plenty of, often you don't need that, because your Lambda function is, pretty much, you've got faith in Lambda that it's going to process this request. And if it doesn't, Lambda's going to do a whole bunch of stuff to say it couldn't be a request and data to queues and destinations and things like that. But
that's a different topic.
Exactly, different. Let's not muddy the waters too much. So that's the sort of asynchronous model. Super powerful for event-driven applications. Then, and to sort of join on to the asynchronicity kind of part is Lambda's got this concept called event source mappings. And this is where we run a service on your behalf called the AWS Lambda Service Polars. And this pulls information from a whole bunch of event sources, and it can filter it, and then it can batch it up, and then again synchronously invokes a Lambda function. So this is super useful if you're using SQS, MSK, even self-hosted Kafka, Kinesis, all these things where you're doing often a bit of big data processing, or you've got a whole bunch of records somewhere. Lambda runs these polars for you. You don't need a fleet of EC2 instances or a fleet of containers to do that. Lambda just handles it for you, and does the filtering, does the batching, and then sends it onto Lambda function. This is really one of the sort of unappreciated, I suppose, powers of Lambda is just having this whole polling mechanism there as part of the service. You don't pay anything extra for it. You pay for Lambda invocations, but all this polling behind the scenes is just part of the service, which is,
And you can do really awesome stuff. For example, filtering the messages for your queues and then batch it in groups of 100. So then you invoke way less times. Or, for example, for Kinesis, it's extremely powerful. If you have thousands of events coming in, then you can package them and process them all together. And you will see why this is important as we move forward.
Yeah, no, it's super useful. I'm thinking, things like ordering, which are important with people, with Kinesis and some SNS 5 things. So yeah, super useful. So let's sort of just jump onto the Lambda then environment lifecycle.
No, you forgot to tell me what is concurrency.
Concurrency. Well, concurrency is the number of Lambda functions that run at the same time. So parallel executions, think of that. And I'll definitely...
Is it the same as transactions per second? Because those are two concepts that we will talk a lot during today.
No, we're certainly going to dive deep into that. And concurrency is related to transactions per second, but it's not the same thing. And so people do get confused about that because people think often when they're building web applications, what is the metric and the throughput you're measuring in is transactions per second. And concurrency is certainly related to it, but not the same thing. But don't worry, we're going to get into some pictures to hopefully explain.
Yes, because those are things that it's confusing. Always. So Lambda invocation, Lambda execution environment. Now.
Yeah, so this is sort of just the understanding the life cycle of what happens with the Lambda function. And basically there's a cold start process and there's a warm start process. Now the cold start process has a few kind of things. There are things that AWS does, and that little sort of isolated micro VM, which is what we call an execution environment. We then sort of download your code, we initialize that, and we get that part ready as AWS for your function to run. Then if you're writing a Lambda function, you've got two parts of your Lambda function. You've got the code that's going to run as part of the invoke, and you've got the code that's going to run as part of the initialization process. So when the function starts for the very first time, it's going to run the initialization process, and then it's ready to run the invoke, which is just a function within your Lambda code. Then what also happens is the next time an invoke comes along, that cold start process has already happened, and we're just going to rerun the warm invoke. Again, I'm going to show you that as well. And so two different sides, the cold start, part of it AWS does, part of it you do in your own code, and then the warm start is the sort of powerful bit, your Lambda invocation.
And one question that I get asked sometimes when I talk about this is like, when I start paying?
Yes. So there is some nuance to this, but a simple way to think about it is if you're using a managed runtime and zip archive functions. So if you're not aware, you can build Lambda functions using a zip archive where you upload a zip file. And if you're using SAM or the CDK or Terraform or Pulumi, you're generally probably using that. It's up to 250 meg. Then there's that part. The other way is you can build it as a container image. You just use a Docker file and you build a Lambda function as a container image. Now, if you're using a managed runtime, so that's things like .NET and Python and Java and Node, thank you, and Ruby. I'm like, oh, that was an important one I missed. Then you basically get 10 seconds of free invocation time. So that is really good.
And that's a lot.
That is a lot, 10 seconds. Now, I said there's a bit of nuance in this because as things have evolved with Lambda, there are some situations where you do pay for the initialization. One of it is if you're using a container image, because we don't really have, because it's all one sort of big blob of storage, we haven't got the way to sort of split out the init and split out the invocation in as neat a way. So when using a container image, that is all charged for. The other one is custom runtimes. So if you are doing some interesting things with custom runtimes, and with Lambda, you can use literally any language if you want. I've written a PowerShell custom runtime. There's things, for PHP, Fortran, whatever.
There is COBOL.
There is COBOL as well, and you do that. And some people also then write their own custom runtimes for even Node or Python because they have some really specific things that they don't think that the built-in Lambda managed runtimes have. If you're using a custom runtime, even if it's Node or Python and it's your own custom runtime, yes, you will be paying for that initialization time.
That's great. So then if you're using custom run, like normal runtimes provided by AWS and you zip it, then you can use those 10 seconds for free in your initialization handle. That means take advantage of it. All the things that can be used and reutilized, put them there.
Yeah, so that's the really good practice is, when your Lambda function in the cold start time, use that. If you've got secrets to download or a database connection to make, or you need to, generate a UUID or I don't know, any kind of setup kind of things, connect to a third-party API, you do that all in your initialization code, and then that's ready to run. And when your invoke happens, and then subsequent invoke happens, that database connection is there. The secret has been pulled from Secrets Manager or HashiCorp Vault or wherever it's come from, and it just makes your subsequent invocations way more efficient and also cheaper.
Yes, so that's a well, my tongue tried to it's a
tips and tricks. There
me.
We go.
Tips and tricks. It's a hard thing for me to say to do. So now we know what is a cold start. We know what is a warm start, and what happens when we have one request coming in.
Okay, ta-da. So let's talk about a sort of Lambda timeline going from sort of left to right as if this was a logical progression. So if a single request comes in, Lambda's then going to run that initialization, that's that cold start process, and then is going to invoke the function. Now, Lambda can only run one request at a time. So this execution environment is actually blocked for this time while Lambda is running this invocation. It can't do anything. There's no concurrent or parallel requests within an execution environment. Lambda's busy doing its stuff. Now, of course, Lambda functions are going to scale up. You're going to have more Lambda functions that are going to be invoked. So if the function is invoked again while a request is still in process, then Lambda is going to put together another execution environment. Another instance is then going to be provisioned. The initialization phase is going to run, and then the invocation is going to happen. So here on the slide, you can see we've now got 3 Lambda functions that are running. Now, when request 1 is finished, you can see that carries on with requests 4 and 5, just the same kind of model. But now when request 1 has finished, it's now actually able to handle another request. So request 1 has done all of its processing, and so when request 6 comes in, it is now warm and free, as we were speaking about earlier, and that can run just the invocation. Doesn't need to run the initialization because that ran as part of request number 1. The initialization code has already run, and so we can just run an invocation. Now, just to note that sort of if you can't see the colors so clearly, the initialization phase is the purple phase and the invocation phase is the dark blue phase, but that timing doesn't necessarily represent what may be happening. It's just a representative of it. The initialization phase could be much shorter, could be much longer. Same with the invocation phase. So it's just an example. Don't necessarily always think that that's the actual timing split, the proportion.
Yeah, it depends.
So
that's great. So now we've got
more requests coming in because we've got a busy website and things are happening. And so that's really cool. And so this sort of process continues as subsequent requests come in. So it's going to reuse the execution environments when they are available. And then it's going to create new execution environments when we need more. And this is actually increasing the concurrency. And you'll see how we're going to measure that a bit later. So you can see here.
And
yes.
How long this warm state will last?
The warm start, it depends on a few different sort of factors, but we keep it around for a few hours. Now, that's there are some other scenarios where we maybe are going to terminate your execution environment earlier. Some kind of things when there are some errors in the service or we need to balance out the fleet. So obviously, one of the cool things about Lambda is it runs across multiple availability zones. If we start getting some hot availability zones, we need to balance some things across the fleet. Also, things go wrong with Lambda. The servers that Lambda is running on, they're going to be faults, they're going to be issues, things are going to happen. So we're obviously going to replace those as quickly as we can, but that may cause you to have some run execution environments that don't hang around as long as you expected.
And if you're using the latest Elias, then when you deploy, then you will basically start again with cold.
So so that's also another thing to bear in mind. When we're talking about all this Lambda lifecycle, this is literally a function version. So if you update your function code, it all sort of starts again. It says, yep, you've told me that you've uploaded some new code. I'm going to start again. Now, saying that, any invokes that are in flight aren't just going to disappear. Obviously, they're still going to be processed, but any new invocations come in will go to the new version, which will then do the cold start process and an invocation, which is pretty much what you'd want anyway.
Yeah, and it's awesome because you don't need to worry about rolling out the update.
Yeah, exactly.
Well, you can do that, but that's a totally different story.
Yeah, you're worried about, I've got 2 different versions in flight at the same time.
You could use co-deploy or something like that if you want to roll slowly, but then we can get it. That's a different video.
So that's using sort of rolling out, and AWS SAM, the serverless application model, has got a really good way to be able to do that. So you can just start at 10% and ramp it up to 50, 60, 70, 80, 90 to get confidence. But that's a choice you're doing. Lambda's just not going to do that.
Exactly.
So let's carry on. Our website is still getting more traffic, and as you can see here, we had some of those warm invocations, 6, 7, and 8, and then a request 9 came in, but we're still busy, and so we had to do another cold start, and then also request 10 came in, and request number 4 is finished, so request number 4 can use request number 4's execution environment and do request number 10.
I think this graph shows why it's so important to have a stateless function, because it's so rare that you get the same environment again. Yeah, exactly. It's just and you never know when it will happen. Yeah.
So you don't want to overplan this and over-prepare this, because a lot of people used to, in the before times, and we're going to talk about provision concurrency later, is think, in order to avoid these cold starts, I'm going to sort of ping or warm up my Lambda functions by running them. And yes, that is going to work to some degree if you're going to sort of do 10 quick requests to Lambda, and then it's going to scale it up, and you're going to hope those execution environments are going to hang around, but you can't guarantee it. And so if it's going to annoy you and bug you that 90% of that, or 80 or 90% of that is successful, and then 10 or 20% is just going to absolutely mess up your application, that's not the best way going to do it. So it's not 100% deterministic. Yes, it's going to help some ways, but we've got way better ways that we can be able to do that. So let's then actually talk about measuring this kind of concurrency. What does this sort of concurrency actually mean? So concurrency is the number of simultaneous or parallel requests and invokes as they happen. So here you can see for a single execution environment, the number of concurrent requests is always going to be 1. If you're going to have request 1, 2, up to 10 million along the pipe, that's literally always going to be 1 concurrent request, because Lambda actually isn't scaling up; it's just reusing that execution environment for warm starts, and so your concurrent request is always going to be 1. But now, with the example before of 1 to 10, the Lambda function concurrency at particular times is the following. And you can see when requests 1, 2, and 3, concurrent requests are going to come. 4 and 5 happen. The concurrent requests are then up to 5. Then as soon as request number 1 is finished, well, that's going to drop down to 1, which allows 6 to start. And as it goes on, and you can sort of see, how the values change, but the important thing to remember is concurrency is literally a point-in-time measurement. So literally taking a quick snap poll of exactly what's going on, and that's going to be your concurrency. And hopefully that makes it a little bit easy to understand, because as Lambda scales up and scales down, because also when runtime environments aren't used for a long period of time, Lambda's going to grab them back, and that's going to then reduce your concurrency. So just think concurrency is a point-in-time measurement of how many parallel requests are coming. Yeah,
that's it. That's important thing. Like if you have, for example, 10 concurrent requests and then you let it for a while, then you might have it just changed with time, because it's not something fixed. And that sometimes we forget. Sometimes we run some tests. Oh, we can run this many functions in parallel, but it might get a totally different number.
Yeah. And also in this whole concept, it's also important to understand, when we were talking about the synchronous and asynchronous requests, that actually a lot of this only really matters in terms of performance to your end users if it's a synchronous request. Because a synchronous request, you're waiting for the Lambda function to come back. So there you actually do care a bit more about the cold starts, because that's actually impacting your performance. anytime you're doing an asynchronous request, whether that's via the SDK CLI or something pulling from S3 or an event bridge rule, as I spoke about earlier, those cold starts really shouldn't bother you, and it's not something you should even worry about, because whether your cold start and your initialization, nothing's waiting for that to happen in terms of holding up your website from processing something else. And so, really the cold start, warm start thing is really only applicable to synchronous functions. And even then, as you may sort of gather, the next sort of way of thinking about it is actually the more concurrent requests you have, the fewer cold starts you have, because the environments are going to be reused. And I think there's an internal stat or something. It's less than 2%, I think, of cold starts for synchronous invocations are less than 2% of requests for synchronous invokes are cold starts. So as the more your application scales up, the fewer cold starts you're going to get. And this is often unintuitive when you are developing an application, because what you're doing, you're writing a Lambda code, you upload a new version of your function, you try it, cold start, try it again, you then scale it up to 5 requests, 10 requests, they're all cold starts. You then upload a new version of your Lambda function, they're all cold starts. You think, oh my word, when my application scales up, this is going to be terrible. But the busier your Lambda function is, actually the fewer cold starts it's going to experience, because once it's ramped up the number of concurrent requests, subsequent requests are going to reuse those execution environments, and your percentage of cold starts is going to dramatically decrease.
And also, this is when load testing becomes very important, because then you will have a significant load, that then your environments will be warm enough and you can see more or less the real behavior. And also, synchronous requests tends to be shorter, so you will have all pile in the same line, kind of.
And also when we're talking about costs and scaling down to zero, this is one of the cool things about Lambda, is you can do these massive tests just to understand it, but you don't have to set something up and run it for an hour. I mean, you could literally, if you're doing a synchronous request, you can bombard Lambda with a huge number of requests and run, 1,000, 3,000, 10,000 requests for 10 seconds, 5 seconds, a minute, if you want to try something out and really get a feel for how your application is going to scale.
Yeah, that's true. I like to use now the artillery library that you can run in Lambda function. So then it's don't do it in the same account, because if you are running a lot, then you might, we will talk about the account quotas later, but...
Yeah, get Lambda to test Lambda. There we go.
Yeah, do it in a different region.
So now we were talking about the transactions per second and the concurrency, and how that.
What is transactions per second? So do we see it now?
So transactions per second is the number of transactions per second. Now, I don't want that to sound flippant. So it's the number of transactions Lambda can process per second, and it's basically the sum, of all the invokes for that period in time. So if a function takes 1 second to run, as in this diagram, and there are 10 invocations happening concurrently, happening at the same time, Lambda is going to create 10 execution environments. And in this case, then Lambda is going to process 10 requests per second. So in a way, the requests per second and the transactions per second are and the concurrency is the same, because each function is going to take a second to run.
But that's not the reality.
Not always. Because now, if we are to half the Lambda function duration to 500 milliseconds, the Lambda concurrency remains at 10. However, the transactions per second is now 20, because you've run 10 invocations of the Lambda function, 10 transactions, but they ran for half a second, and then you're going to use the warm start process and run 10 invocations again. So in that period of time of 1 second, you have now run 20 Lambda functions, and so that's 20 transactions per second, even though your concurrency never went above 10. Obviously, if your function then takes 2 seconds to run, would look a bit funny on this kind of timeline. But then, during the initial second, your transactions per second would actually be 0, because nothing's finished doing it. But then over time, if you worked out your average, then your transactions per second would be 5. So that's how you would work it out. And you can use CloudWatch metrics to look at all of this. There's actually a metric name called concurrent executions, and then you can view the concurrent invocation for an individual function or all of your invocations.
Is this something we should look account-wise, or it's very important per one function or for all the functions in our account or region?
Both are important depending on what you're going to be looking at. I'm going to cover shortly, but there are some limits. There are some what we call quotas for how some of this currency works. And in fact, if I just bring up a little graph over here, the actual there is an account concurrency, which is the number of concurrent Lambda invocations that can run for your whole account. And so that's per account. So much when you were talking earlier about having multiple accounts, this is just another one of those reasons to have multiple accounts, because if you have your production environment and your development environment in one account and you're doing a huge big load test in your development environment, your production environment is not going to have its happiest day. So again, one of the reasons to split things out with accounts. But also this account concurrency is not a fixed number. The account concurrency starts and you can expand that. But if you think
it's a soft limit.
But if you think of that in a pie, that's sort of how it works from the concurrency limit. Just pause in your mind the reserve concurrency. Don't get too confused about that. But if you think of the whole reserve concurrency within an account as this whole pie, and we've got 3 different functions, and they can then remove concurrency from that account as it's being used up. And then this thing called reserve concurrency, and this is where you can then basically guarantee an amount of concurrency for an individual function. So that can be a set value, and that means that Lambda function can always run that amount of concurrency. You know, whether it's 1,000 or it's going to be 10,000, it's still going to be able to run that concurrency. So 2 parts: it's going to reserve that concurrency from the account concurrency, so it's guaranteed for that Lambda function, and then that Lambda function is always going to have that account concurrency available. If you then deploy another bunch of Lambda functions into your account and they scale up, that original Lambda function will be protected. Your new Lambda functions could get throttled if you then go above that level.
So throttling will happen. I think that's an important concept, that when we don't have enough capacity in our account.
Definitely.
And what is the default that we have in our accounts?
The default concurrency is 1,000. So each Lambda function has each account concurrency is 1,000, but that's a really soft limit. And as I mentioned before, this can be increased up to sort of hundreds of thousands.
And you can increase it making a ticket in support.
Yeah. So the service quotas console allows you to do that, and it's a really simple process. Obviously, the bigger your account concurrency you do request, there may be some conversations just to be had with the Lambda team, and this is for 2 reasons. One, it's to sort of help make sure that you understand your concurrency, because obviously there's a cost involved with this. If you're going to request 10 million concurrency or hundreds and hundreds of thousands of concurrency, AWS doesn't want you to sort of step on your own toes and cause yourself to have an issue. And also, we do need to do some capacity planning within the Lambda service, and we've got to be able to, one of the magic parts of Lambda is this amazing scaling, and obviously we need to have those servers under the hood to be able to do all of that. And so we just want to help you to understand what your concurrency is, and there's some really good learnings that we can help you as well via the whole support process to say, well, have you thought about this? Have you thought about doing different kind of things to make Lambda cheaper for you?
Yeah, and I think I always say that it's a safety mechanism, because it's like a limit. If for any reason your Lambdas get crazy that you don't know what you're doing, you cannot run more than 1,000 at a time.
Yeah, and also there, weird things that people can do. You can have infinite loops that people create.
Yes.
So, a Lambda function that runs off an object being uploaded to S3 and then writes an object back to S3, via SNS, these kind of things. So those are the kind of, and, we do have some protections in place to be able to, try and monitor and sort those things out, which you can look for. But, for a runaway function with, hundreds and hundreds of thousands of concurrency, that may not be the happiest day for your finance department, at least. Never mind the performance of your application.
Yeah, exactly.
Yeah. So we were talking about the reserve concurrency and the throttling, and so the reserve concurrency in terms of guaranteeing that the function can always scale up to the reserve concurrency amount. But there's also another really cool use case for this, and this is to protect downstream resources. So if you've got a database or an external API that can maybe only handle 2 concurrent connections, you could also ensure that Lambda can't scale beyond 2. So this reserved concurrency is going to protect the concurrency, but is also going to not allow anything beyond 2 concurrent invokes. And so you can use this to make sure that Lambda doesn't overwhelm the downstream service. And you can then also use reserved concurrency for other use cases to invoice sort of race conditions. So you can make sure that your function can only run one concurrent invocation at a time. That's a useful thing. And then you can also set the reserved concurrency to 0. And this literally stops any function invocations and just acts as an off switch. And this can be super useful to stop Lambda invocations when maybe you've got an issue with a downstream resource. And what it can do is it can give you some time to then fix the issue before removing or increasing the concurrency to allow invocations to continue. So if you are pulling from an SQS queue, or you're pulling from Kinesis, or specifically in the polar kind of model, obviously if you're using the synchronous model and you stop Lambda invokes, your front end or whatever is going to
we'll get an error.
Is going to get an error or have a happy kind of thing. But for the sort of asynchronous and the polar things, this is a really nice way that you can just say, I got a problem, pause, fix whatever's happening on your back end, and then start Lambda up again, and that'll start pulling things of SQS and Kinesis. I mean, there's a whole concept of visibility timeouts, but let's assume that's all configured correctly. And then if you're reserving concurrency in the red box on number 3, you can see that as the throttle, and then Lambda is going to give basically a 429 response back to whatever it's calling Lambda.
Yeah, and that's important to also make sure that you check if you are throttling requests.
Yeah, and you can monitor that as well.
Your alarms, and there is a metric for that. And then there is another quota. Do you want to talk about that?
There is another quota, but I just before I get to that, because when we're talking about the scaling, is when we were talking about the cold starts and the warm starts, is this provision concurrency. And provision concurrency, it's a super useful thing to use. Because obviously, when we're talking about cold starts, mainly for synchronous requests, obviously this can introduce latency for your applications. What you can do is you can reduce this latency by configuring provision concurrency for a particular function version or alias. Needs to be a particular version or alias. It can't be the latest version. So if you're having some weird things that you don't know what's going on, that's definitely the first thing to check. And what this does is this prepares the runtime environments in advance and then runs that function initialization process, runs the cold start process in advance, but doesn't actually run the invoke immediately. And so it's ready to invoke when it is needed. So what do you do if you are expecting some traffic spike? Say you can say before 9 o'clock in the morning or something, you can set your provision concurrency up to 1,000 concurrent invocations. That's going to run that whole initialization process. As soon as your awesome, amazing sale kicks off at 9 o'clock in the morning, you're not waiting for any cold start process. The invoke can happen immediately. And obviously, this is super useful for languages and runtimes and code that you have that has a longer cold start duration, and you really want to banish those cold starts entirely. Again, you shouldn't really worry about this for asynchronous invocations. It's more for synchronous invocations.
And this means, for example, because in the case of reserved concurrency, we are throttling, but here imagine that a number 11 comes, but number 1 has not finished, then it will just get a cold start.
Yeah, so that'll get a cold start. So it can, they can work in conjunction.
Exactly.
Additional Lambda scaling will still work. So if you do have request number 11 coming in, you will have the cold start, but you've got the sort of the army there already running. And the cool thing is you can actually use application auto scaling to adjust the provision concurrency. So you can even do this automatically based on Lambda's utilization metric. So that's sort of a nice dynamic way that you can actually then configure your provision concurrency. So you sort of ready, and when you're getting up to maybe 80% or 90% of what provision concurrency is being used, well, you can then scale up in advance of that next batch.
That's interesting.
Yeah.
So you can be warming up as you need.
Definitely. And then just before we get onto the quotas, concurrency, it's worth understanding how it does work differently across the invocation models. Now, if you've got a synchronous and asynchronous invocations, so this is via an API or even an event trigger, SNS, S3, Event Bridge, whichever. There's really a one-to-one mapping between the event and how it is processed by the Lambda function. And then concurrency is going to increase to handle, but remember they are individual requests. And then there are two different sort of other nuances to understand. One is when using an event source mapping as part of a polar, and when you're pulling things off a queue like SQS. Now, whatever's producing the messages are going to place those messages individually on the queue by whatever application. But then the Lambda server's polars are then going to grab those messages off the queue, and it's going to batch them. Remember that diagram earlier when we did the filtering and the batching? It's then going to then batch them and then send that whole batch to your Lambda function. So your Lambda function is going to receive a batch of messages, which it's going to process as a single event. And then your Lambda function is then going to iterate through those items. So that's an interesting thing to think of, that even if you are scaling up to super duper great heights, you don't have to scale up Lambda per individual item that's landing up in your queue. SQS can batch things up, and I'm just missing off the top of my head how big a batch can be, but I think it's something like 10,000 items in a batch or something like that. So, I mean, it is huge. So if you think 10,000 items in a batch, and each batch takes 1 second to process, that's 10,000 transactions per second that you are processing. So this is when Lambda can get super duper.
Yeah, and it becomes. I have run some demos, for example, with Kinesis. It gets crazy, like the amount of scale so fast when you start just invoking 1-to-1, and then it just comes so much down when you start giving 100 or 1,000 batch groups. It's just your concurrency stays very low, and it's everything under control. So it's something as simple as just adding those zeros in the in the event source.
But it's even interesting, even for the queues, because there's obviously you can control your concurrency, and if you are reading off a queue and then you're sending it to a downstream resource, a database that can only handle 50 connections or that kind of thing, there are ways to then control that concurrency, and that's part of the sort of visibility timeout, where if there is a throttling, Lambda is going to throttle and it's going to put things back. The SQS queue is not going to be deleted from the SQS queue, and it's just going to keep retrying until that throttle happens. So that's why your visibility timeout needs to be big enough to handle those multiple retries. Now, people often go, "Oh, that's slightly freaking me out because Lambda is throttling it." Yes, Lambda is throttling it, but if your visibility timeout is long enough, Lambda will eventually get to process those messages, as long as obviously whatever you're putting on the queue is not faster than you can drain them off. So if you've got a huge dump of records, it's midnight at night, and someone's put 1 million records on an SQS queue. But you can only support 1,000 downstream connections. Well, your Lambda will throttle, but it's still going to keep going back, and it's eventually going to process them all. So when it's throttling, it doesn't mean it's not being processed. It just means, hang on, I need to wait. Calm down, and that processing happens. So that's very powerful with SQS. That even though if Lambda can't fully drain the queue in immediately, it's going to get there. You're going to see the throttles, but if your visibility timeout is big enough, you're still going to have all. But
that's really great for services, for example, that spike.
Yeah.
And then if you have an event-driven architecture, other parts of your application might not need to spike. They just have this buffer, and they can take the messages and process them asynchronously. And when they're ready, they will. Maybe what happens is that if you have a spike in orders, then your customers might take 5 minutes to get their order confirmation email, but eventually it will happen.
Yeah, and that's a sort of super powerful part about the sort of event-driven architectures and being asynchronous. That how many batch processes do people have where they upload a huge amount of files or a huge amount of events or something at some point in time, and then you don't have to scale your downstream resources to handle that. If your external API can only handle 50, 20, 1,000 concurrent requests, that's cool. Set your Lambda concurrency, and Lambda will eventually drain those SQS messages, and it will get to it eventually, and you're not having to scale up all of your application, as you said.
Yeah. And one question, because there is the Lambda that letter queue, is that coming into place here? Things are throttled?
Not from the throttling, but if your visibility timeout runs out, then Lambda is going to put it in the dead letter queue. Now, also, you configure the dead letter queue on the event source mapping, not actually on the Lambda function, because what's going to happen is the event source mapping is the polar resource. That's the internal Lambda thing behind the scenes that you can't really see, and that's what's pulling the records off SQS. So you configure the dead letter queue there, and if the visibility timeout runs out, then it's going to put messages on the dead letter queue. So if you are configuring reserve concurrency and you're limiting the number of Lambda functions you want, your visibility timeout needs to be long enough that those retries can keep happening. And you don't want things in your dead letter queue. So you want it.
But it's good to have it.
Absolutely, because if there are failures or something happens, and you've got maybe you've got a poison pill message, or if you've got something weird with one of your events, you never want to lose that. But then you want to only use it for sort of a manual check of, let me have a look.
Exactly.
Let me have a look at that. Yeah. And then just quickly, the streams works in a sort of similar way, but obviously streams are slightly different from queues, and sort of Lambda has a function that runs per shard of that queue, because obviously things with streams, ordering is important. So something like Kinesis, each shard, everything within a shard is in order. And so you will have a Lambda function per shard that will process the items in batches of that shard in the order that they sent. So you can maintain the ordering per shard. This isn't going to be the ordering across the whole stream, but per shard. And people who use Kinesis and MSK and Kafka and all those kind of things are used to, when they put something into the stream, they specify the shard they're going to put it in, or the partition they're going to put it in, and then Lambda's, is very clear that there's a one-to-one mapping, and so it scales up that way. Lambda, you can then have enhanced fan out for some kind of things, so that messes up with the ordering, but basically Lambda's going to be able to scale up to whatever you're going to need.
So that's good to know. So now we understand how things scale, we understand the concurrency, we can see it maybe in action in an application or something.
And just because when we're talking about the quotas, so we got the burst concurrency quota. So this is when a Lambda function initially starts, by default on all regions, you get 3,000 burst concurrency. Sorry, not in all regions. The big regions, you get 3,000 burst concurrency, and then 1,000, and then down to 500 in some of the other regions. So this means without you pre-planning, without you doing anything, forget provision concurrency, any of that. If you want to run 3,000 concurrent Lambda functions in some of the bigger regions, off you go. There's no limit, nothing like that. Anything beyond 3,000, yes, you are going to be limited. And there's actually, at the moment, there's no, that's a hard limit. So you can't, there's no way to sort of fudge that limit or do that or increase that. Now, after your initial then burst, after that, your function can then scale by 500 instances each minute. And I'll show that in a nice graph, which makes that more easily understandable.
Yeah, I think this is a weird concept, this what you mean, the burst concurrency. At least when I saw it the first time, I was like, what is this?
Yes, so this allows your function to go from 0 to 3,000 at the same time without any pre-planning.
It's like all the functions at the same time hit start and boom.
Off you go, exactly. So you can think, so obviously provision concurrency is all cool, but you need to have pre-planned all of that. Sometimes you're not going to know what's going to hit your website or how many requests are going to come in. So if you have between 0 and 3,000 initially, there's nothing you need to worry about for your concurrency. It's just going to scale up. With the one caveat that 3,000 is shared across all functions in an account. So, obviously this is all a shared resource. That little pie chart diagram I was showing also applies to this burst concurrency. And then the account concurrency quota, that is the pie graph. And this was the default 1,000 per account, and this can be increased up to hundreds of thousands.
Yeah, and this is all per account per region.
Yeah, exactly. So I mean, we've got cool customers who, if you think about it, now top of my head, I don't know how many regions we've got.
27,
27,
26, 28, depending on
tomorrow.
what we announce something when this video gets out. I don't know.
Exactly. So think of a sort of mathematical model that, 3,000 in burst concurrency across some of the regions, thousands for some of the others, and 500 for all of these. I probably should have way clever and worked this out all in advance. But you've got many, many, many thousands of concurrency you can spin up if you wanted to use all your your burst concurrency across every single region. Can you imagine? And come to think of it, if Lambda has up to 10 gig of memory, which gives you 6 virtual CPUs, I mean, we in terms of virtual CPU cores and a distributed massively parallel scalable service, you've got tens of thousands of CPU cores available to you immediately without any planning, and you pay by the millisecond. That's pretty cool.
It's pretty awesome.
That is pretty awesome. So let's see how this all sort of works together. So the following is going to work through how the account and the burst concurrency work for an example application. Now, we've got some good application builders, and they've been anticipating handling some additional load. So what they've done, that line on the top, is they've raised the account concurrency to 7,000. Now, there are no other Lambda functions running in this account, just to keep this simple. So this function can use all the available account concurrency. So the clock on the bottom, you can see it's just before 9 o'clock in the morning, 8:59, and the application already has a steady stream of requests. It's using 1,000 concurrent execution environments. And so let's say each Lambda invocation takes a quarter of a second, 250 milliseconds to run. So quick maths on the back of an envelope, your transactions per second would be 4,000. 1,000 concurrent runtime environments. Each of those runtime execution environments is going to run 4 times in the second. You've then got 4,000. That little white dot over there, that is the burst quota available. So this is in a big region. So we've got 1,000 burst quota.
No, 3,000.
3,000, sorry, 3,000 burst quotas. Too many thousands you're talking about. Marsha's on the ball. I like it.
I'm listening.
So 9 o'clock in the morning, there's a large spike in traffic. We've got 5,000 new sustained requests come in. Immediately, you can see all of that burst quota available drops down to 0. And you can see then 1,000 requests is going to use the existing execution environments. They're already there. They're just going to get the next invoke.
And they're warm. They're ready. They
are built for this. They are primed and ready to go. They're excited. And then Lambda uses the 3,000 available burst concurrency, which we had, to increase new execution environments to handle this additional load. But 1,000 requests are then going to be throttled, as there's not enough burst concurrency to handle all 5,000 requests. So you're going to have 1,000 that are throttled in the red and white on the top, but you're going to have 4,000 requests that are going to all work. And what does that mean? How many transactions per second? 4,000 requests, 250 milliseconds each. So that's 16,000 16,000 transactions per second. So within 1 minute, we've gone from 0 to 16,000 transactions per second in this application. And we haven't really configured much at all. We're just using the burst concurrency and existing execution environments. So 1 minute past 9. Another minute has passed. So this means we've got another 500 burst request available, and Lambda's going to then be able to then scale to handle another 500 concurrent invocations.
Why we have 500?
Because once you've used the burst concurrency, you have 1,000, and then each minute later you get another 500.
Okay.
So that's the way the sort of gentle scaling works up. You got your initial burst, and then you get the 500 that burst up in advance. So we've got 500 concurrent invocations per minute. 500 requests are still throttled because we haven't been able to handle that. Another minute goes by. We've got now another 500 burst quota, which is being made available. And then now this means that no further requests are throttled. The application can now handle all 5,000 requests. And you can see the little white line on the bottom that means that in the next minute, we're going to have another 500 burst concurrency. So if your application was steady state from here on, you would have no problem. You'd just be using warm execution environments, 5,000 sustained requests, off we go. But we are busy. So the application does continue to handle the 5,000 requests and that burst concurrency 500. Yeah. So then, at now 4 minutes past 9, the application sees another spike in traffic, and this time it was unexpected. So our clever application builders who built that 7,000 or configured that 7,000 account concurrency are a bit caught out, don't quite know what's going to happen. Oops, we've had a great sale, whatever's happening. But now, so this is then 3,000 additional sustained requests that are going to arrive. So it's good. So that's going to then be a combination of 8,000 requests. 5,000 are going to use the existing execution environments. And then Lambda, because 2 minutes have gone, Lambda is going to now use the available burst concurrency of 1,000 to create new environments to handle the additional loads. But 1,000 requests are still going to be throttled, as there's not enough burst concurrency. And then another 1,000 requests are going to be throttled because we've gone above the account concurrency, and that has been released. So whatever related to the burst concurrency and concurrent requests, we can't ever go above the account concurrency quota. Now, obviously, we can raise that, but we've got a big sustained request. We haven't. This is unexpected, and so that would be throttled. So then in the next minute, 5 minutes past 9, we've then got that other 500 concurrent requests. Application can now handle 6,500 requests. Still 500 requests are throttled. Is there not enough burst concurrency? And still 1,000 requests are throttled as the account concurrency quota has been reached. And then eventually at 6 minutes past, another 500 requests. Now the application is able to handle 7,000 requests. 1,000 still being
that's the maximum,
and that's the maximum. And so now this would be the steady state that would carry on, and the application at 7 minutes past will be able to continue to handle 7,000 requests. 1,000 requests are still always going to be throttled because the account concurrency quota has been reached. And if people have been dying to work out the transactions per second, well, we've got 7,000 concurrent requests, a quarter of a millisecond each, a quarter of a second each. So that's literally 20,000 transactions per second. So we've literally scaled from 1,000 concurrency to 7,000 concurrency, 4,000 to 28,000 transactions per second within 7 minutes. So that's pretty good scaling. And remember, all of this you could do in advance with provision concurrency. So you could do the 7 minutes, starting at 8 minutes to 9, and build this up using provision concurrency in the same way. If you configure your provision concurrency, it still uses the same scaling quotas, uses the same account concurrency, and that takes the same amount of time to ramp up.
Yeah, if you knew that you will get like 7,000, then maybe that's something you can pre-provision.
So that's where you'd use the application auto-scaling. At 9 o'clock in the morning, you're going to get a sustained burst of 7,000 requests. So you then would all configure this in advance. And as your customers hit your website at 9 a.m.
And you will not have any burst throttle then.
No. If you had the 7,000.
Everything will be.
But now think of how sort of adaptive this is, that provision concurrency you do pay extra for. So you are going to pay to have, but it's not as much as it would be for a whole invocation request. But if you've got 7,000 or whatever value you're going to have, and remember, it's not 7,000 concurrency. This is 28,000 requests per second. So if you think, I'm going to have maybe 27,000 requests per second, let's have a little bit of buffer to be nice, I can use application auto scaling literally within a few minutes before 9 o'clock to set that up. I'm not having to spin up an EC2 instance or do a whole bunch of containers. Even if they're serverless containers on Fargate or other kind of mechanisms, that's still going to take time. And so you can do your 28,000. Maybe you're going to have this massive fire sale. You're selling tickets for a concert or something, and you literally know that within 10 minutes, all those tickets are going to be sold. You can just turn that application auto-scaling down, and you no longer pay for it. So, this is a really adaptive way that you'd be able to scale up your Lambda functions.
Yeah, that's very powerful. But then that needs some planning ahead.
It does need plans. We try to give you some of the levers that you can use the burst concurrency and the account concurrency to not have to plan. But if you and again, remember, this is also only for cold starts that you care about. All of this, all the provision concurrency and cold starts doesn't matter for asynchronous. Of course, the burst concurrency and account concurrency does work. But as we're talking, about with SQS, you're going to get some throttles, but you've had a big dump of data. If your visibility timeout's long enough, they are going to get processed anyway, and you're all good.
And you can still, like all these things, they have alarms. Well, you can build alarms. You have metrics. You can build alarms upon those metrics. And then if you have an application that get that many requests per second, transactions per second, it's an application that that you have been working on. So it should not be it can be a surprise in the sense of unexpected events, but in the sense that you might be able to see it, so you can at least have some planning around.
And there's specific metrics. For instance, Kinesis has the iterator age. So there's literally a metric of how far behind am I. So you can, watch it up, and you're going to know, well, I'm getting a bit behind, but I know I'm not going to get more sustained data, so I'm going to get a bit behind, but I know I'm going to catch up. Lambda's going to scale up. But if you're going to have sustained throughput, well, then you can do different kind of things. And things like Kinesis, you can add additional shards, and then that Lambda is also going to scale up automatically based on the number of shards. Yes, you need to have the account concurrency to handle that, but you've got lots of ways that you can do this.
And can I, because you mentioned like the transactions per second, the concurrency, if I make my functions faster,
yes,
will that make everything easier?
It will make everything, makes everything quicker, which makes everything cheaper, and so you get more transactions per second. So yes, if you say we had 250, let's think of my math. So if we had 250 milliseconds that a function takes to run, and so we have 1,000 concurrency, that means you have 4,000 transactions per second. If we are able to then reduce that invocation time by 50 milliseconds, now it's going to be 200 milliseconds to run. That means you're going to be able to run it instead of 4 times in a second. The function is going to be able to run 5 times in a second, so you can have 5,000 transactions per second. So
and you will reduce the amount of concurrent invocations.
And even if maybe you'll reduce concurrent invocations, but even if you don't reduce concurrent invocations, your transactions per second you can have a dramatic impact on. And so this, depending on even languages you use or the amount of code or how efficient your code's going to be, all going to make a difference if you want to get really efficient as possible.
So again, back to load testing. If you really need to understand this for your application, run load test. It's pretty straightforward. Graph it and understand the different variables that are the speed, like how fast your application runs, what are the different metrics that are impacted, how they're impacted, understand them, and then you can play and tune them. And sometimes, as you said, it's not expensive to give more memory that will give more CPU that will make the function run faster, because then you might be able to increase everything.
Yeah, that's a good point. So we didn't go into deep enough of that. With adding more memory to your Lambda function also adds more CPU, and maybe if it's memory bound or CPU bound, adding just a little bit more memory could have a dramatic effect on the finish time of your function, which can also impact. But also, we've been talking about a lot of big numbers, but honestly, most web applications out there really aren't using anything like this. And I can't even pick a figure out of thin air, but if your web application is receiving even 300 concurrent requests, per 300 concurrent requests, that's a decent kind of website. And we're talking about 300. That doesn't even get to anywhere near the account concurrency or the burst concurrency or anything. So this is all for high scale.
I have done an example with my lift and shift. It was kind of funny because I have every invocation that you do in the website. Lift brings a new Lambda environment, runtime environment. So every click, it's executing a new Lambda function. So basically, any customer will run hundreds of them without really realizing. And when you run load test, you can really get to the 1,000 concurrent. It was the first time I was easily getting there, because before it was like, okay, just calling the backend. But now if you call everything in your website, it's just, it's very easy to get there if you are doing something like I was doing that. I don't know if it was right or wrong, but,
but it worked.
I was just doing it.
But the thing to bear in mind, really, the bigger picture is people all think, oh, well, Lambda can't scale or whatever. We've shown Lambda can scale, but generally for a lot of workloads, Lambda's going to scale well enough for you. And, most websites out there, and even, internal APIs, if you think you are running API gateway in front of Lambda, because we're talking about synchronous requests for this as well on the scale up, or you're using Lambda function URLs or whatever, like, honestly, do your metrics on what you're running at the moment. How many concurrent requests is your website hitting? Internal website to get up to the thousands, tens of thousands, you're going to be doing a lot of traffic, and that's not necessarily normal. And maybe there are other things you're going to do to be able to reduce that amount of traffic. So Lambda does scale up hugely, and don't be worried about that. But for a lot of what you've spoken about today is for good information, and it's really important to understand it. But a lot of applications really don't need this kind of scaling up. But it's there for you if you need it.
No, but I think it's good to know.
Because a lot of people,
you are really thinking
a lot of people,
the long run.
When you're designing applications, are thinking, well, what's going to happen when I've got 10 million people, connecting to my application, I'm going to be super successful. The thing with Lambda is you can start small because you're paying for what you use, and you just keep growing and growing and growing and growing. And yes, maybe Lambda won't be able to handle that, but then you've got way other kind of problems to be dealing with your application. So yeah, I would go that Lambda can scale up for literally pretty much anything you can throw at it, and start that first. Don't try and think of when you're going to scale up to your 10 million concurrent requests or 10 billion concurrent requests. That isn't going to be likely. Start with Lambda and then make the hard choices to do something later. And I promise you're going to have way bigger problems of writing to databases or doing network connectivity or managing state or any of that.
Yeah. Yeah, I think the next talk for a totally different video is like handling that problem. Yeah. But I think a lot of that can be solved by asynchronous.
Yeah, definitely.
I think at the end of the day, it's like make your request with your front end, and then from the first layer back, it's all asynchronous.
And it's a simple way to even think about it: the sort of store and process and separate their different thing. And so, from a synchronous request, you can get a really fast response from Lambda, and then all of that code that already writes it to another database and then does a secondary copy and then does the email verification and does all this kind of thing. That can be all stripped out from that synchronous Lambda function, can run behind a queue or something that can keep on processing. Yeah. And your synchronous request is literally as quick as it can be to get the minimal amounts of information back to the front end so it can carry on processing.
Exactly. And I think with that, I hope people now are more happy and feel more confident with their scaling, the cold starts that I don't know, Lambda has like 7 years, 6 years, and I don't know, something like that, more.
8 years of reinvent the server.
8 years, yes. Oh man, time flies. And people still figuring out cold starts. And yeah.
Let's not say that cold starts aren't an issue, but really the percentage of cold starts for synchronous invites is tiny. The more your application scales, you've got less cold starts. There are so many optimizations you can do to remove your cold starts. We haven't even spoken about any of the code ones and SDK choices and language choices. Yeah. And there's, Lambda is doing stuff all the time to remove cold starts. Behind the scenes, we've got, the invoke path and everything. We are shaving off, milliseconds all the time to make it even efficient. So that's the stuff that we can do. There's a vast amount of stuff you can do in your code as well. And, coming out, Lambda's always adding new functions and features and all those kind of things. So, even for those outliers where cold starts is an issue, there's always going to be optimizations you can do.
Yeah, and that's the magic thing of when somebody else is managing the infrastructure.
And this is all multi-AZ for you as well, massively scalable across availability zones. You're not even thinking about, is my Lambda function able to scale in that AZ? Do I have enough capacity if one AZ fails that it can scale over into another AZ? You're not handling any of that. No. So never mind all of this individual scaling. This is multi-AZ as well, which is super powerful.
Exactly. And I think with that, I will say thank you, Julian, for chatting with us today and sharing all this cool information with lovely drawings so people can really visualize it and see it. And if you want to read more, I will link the blog post where I found, I saw that you were writing this. It's I'll put this on my channel. If you want to share it around and you're more a reader and leave it in the description box, and also Julian's social media and all that, so you can reach out to him. And
no, perfect. And
keep on touch.
For even more best practices, it's going to be reInvent 2022. I've got 2 talks. One is on serverless general best practices. So there's, this is going to cover some of this, which is super useful to know. And then a proper deep dive into Lambda. So we're literally going deep underground into deep as how Lambda's working. So have a look at those.
And those are breakout sessions.
Yeah, those are breakout sessions.
So they will be in YouTube.
Exactly. So that's why I'm mentioning it. If you're not there, you're not just missing. But I'm always happy to talk. I love talking about Lambda. I think it's awesome. So, and I'm available on social media, LinkedIn and Twitter and whatever. Any other questions or any other nuances, please, happy to chat.
Good. Thank you, Julian.
No, Marsha, thanks for the opportunity. I've been on FooBar.
And thank you everybody for listening until the end. And I see you in another episode of FooBar. Ciao, ciao.
Bye-bye.